This video will discuss the partition function of a system of n independent molecules. So our partition function, as has been the case throughout this entire chapter, is a sum over all energy levels of the degeneracy of that energy level, G sub I, times the Boltzmann factor of that energy level, e to the minus beta E sub I, where beta is 1 over kT, E sub I is the energy of that energy level, and the degeneracy is the number of unique states in that energy level. We saw that our partition function for a molecule is the product of the partition function of its translational, rotational, vibrational, and electronic contributions. So now we're going to go from an individual molecule to a system of n molecules. So if I have a capital Q here for the entire system, usually I'm going to indicate a system of particles by some capital Q and a single particle by a lowercase q, but that's not always the case, but more often than not that'll be the case in this playlist. So big Q is equal to a product of the partition function of molecule 1, molecule 2, molecule 3, etc., all the way up to molecule n. So it's a product from I equals 1 to n of the molecular partition function, which is just Q mol to the n. So if our particles are non-interacting with one another, then we get this nice kind of simple expression. So that would be all good and well, and we'd be on our way. That'd be a system of distinguishable particles where we could tell which molecule is which, and Q, big Q would just be little q to the n. One problem is that for molecules, they're often very, very small, and there's a lot of them, and they have a lot of energy states accessible to them. So what happens is they end up having a property which is called indistinguishability. So we don't actually know which molecule is molecule 1, which one's molecule 2. They all just kind of jumble together. We don't know which is which. So when they're indistinguishable, what happens is this type of an expression actually overcounts the number of possible ways we can arrange our energy, because we don't know what molecule 1, what energy it has. We just know how many molecules have that specific energy. So for example, if we have a molecule with E1 and a molecule with E2, well, it could be molecule 1 has 1 and then molecule 2 has 2, or it could be the reverse. There are 2 ways or 2 factorial ways to arrange that situation. If there are 3 molecules with different energies, there are 3 factorial or 6 different ways to arrange that. So what we're actually doing is we're overcounting by a factor of n factorial when we have the molecules as distinguishable particles. So atoms and molecules generally being indistinguishable particles, what we do is we put a prefactor here of 1 over n factorial in front of our system partition function. So our system partition function there is going to be 1 over n factorial q to the n. And generally we'll tack that 1 over n factorial into the translational component. Okay, so if we take our q cis and we make it a product of the translational, rotational, vibrational, and electronic components of the total system partition function, what we get is big Q trans is v to the n over n factorial, 2 pi mkt over h squared to the 3n over 2. So this is taking the translational partition function to the nth power and multiplying times 1 over n factorial. So just the typical v, 2 pi, mass of particle, Boltzmann constant, temperature over Planck's constant squared. The rotational partition function, if you're significantly above the rotational temperatures, will be T over sigma theta rot to the n, sigma being the symmetry number, 2 for homonuclear diatomics, 1 for heteronuclear diatomics, and a more complicated value for polyatomics. For nonlinear polyatomics, it was 1 over sigma to the n, pi t cubed over theta A, theta B, theta C to the n over 2, each of the rotational temperatures. For vibrations, we have a product of all the individual vibrations, 3n minus 6 for nonlinear molecules, 3n minus 5 for linear molecules, of e to the minus rotational temperature of that mode over 2t over 1 minus e to the minus rotational temperature over t, all of that to the n. And for our electronic partition function, the degeneracy of the ground state to the n times e to the n dissociation energy over kT.